Okay, I'm Subhabrata Barman. I'm an assistant professor in the Department of Computer Science and Engineering at the Institute of Technology. Today I'm going to deliver a lecture on compilers. So basically what are compilers? Uh, when we write programs, generally write programs in high-level languages. So the source code is actually written in a high-level language for user convenience. Now, what computer does is it translates these instructions written in high level languages into its equivalent machine language. So, this machine language or this machine code is for machine convenience. Now, we actually know, we are aware of machine architecture or computer architecture. We have general purpose registers in our microprocessor. We have general purpose registers and floating point registers. And we have the arithmetic logic unit and the floating point unit. And we have other registers and latches, the program counter, the instruction register, the program status word, and the stack pointer. So you can see here in the slide, uh, there is a snapshot of the machine code or the assembly code. Okay, so which is machine uh, dependent. Okay, so we should be aware of the processor architecture as well. So you can see this machine code, these are opcodes and these are, so this is an assembly code. Here these are mnemonics. Okay, so this is the assembly code that is actually generated by the compiler. So the compiler actually translates the source program written in a high level language, which is for the programmer's convenience, and it translates the source program into an equivalent uh, machine code that is understandable by the machine. Okay, that is the assembly code. So therefore, compilers are language translators. Okay, so programming in so what is the disadvantage of programming in assembly code? The disadvantage of programming in assembly code or the machine code is that it requires memorization of the binary codes, okay, which is very difficult for the uh, users, okay, high level users or the program writers. Hence, we require a translator that is capable of translating the source code, which is written by the programmers in high level language, into an equivalent machine code. Okay, so therefore, a compiler is a software, a system software, language translator. What is the task of the compiler? The task of the compiler is to read the program in one language, that is the source language, which is a high level language, and it translates the program into an equivalent code in machine language, that is the target code. Okay, so the compiler translates the source program, which is written in a high level language, into its equivalent target program. Okay, and it also reports any errors in the source program that it detects during the compilation or the translation process. So we use compilers for generating the target code or the target machine language program from the input high level program. Okay, so the target program is used by the user to generate output from the input. Okay, so this is basically the block diagram of the structure of the compiler. So we have the source program which is taken as an input. Okay, and the compiler generates the target code which is generated as output. Okay, and this is the block of the compiler. Okay, and the compiler has the front end part and the back end part. Okay, so the front end uh, actually does the analysis of the source program and the backend actually does the synthesis of the target program. Okay, so the analysis actually breaks up the analysis phase, breaks up the source program and imposes certain grammatical rules on them. So that is the function of the front end of the compiler, and the back end uh, constructs the target program, synthesizes the target program or the assembly code from the intermediate code. Okay, so the intermediate code, intermediate representation, and the symbol table is used for generating the target assembly code. So the front end of the compiler generates the intermediate code. It detects the errors in the source program and constructs the symbol table. Okay, now these are the different phases of the compiler. So the compiler actually scans the uh, input uh, code, program code. Okay, so the input program code has a stream of characters, and that is actually scanned by the lexicon analyzer, which is the first phase of the compiler. Okay, the first phase of the compiler is therefore known as the lexical analyzer or the scanner. So it scans the source code, the characters in the source code, or the character streams in the source code, and it generates the tokens. Okay, so the tokens are actually taken as input by the syntax analyzer or the parser, and it generates the syntax tree. The parse tree is actually generated, and thereafter the semantic analyzer generates checks the semantics and generates the syntax tree. Thereafter, the intermediate code generator uh, generates the intermediate code. Okay, so basically, the lexical analyzer, the syntax analyzer, and the semantic analyzer, these three phases actually make up the front end of the compiler. Okay, and the the machine dependent independent code generator, the code generator, and the machine dependent code optimizer, these actually make up the back ends of the compiler. So the front end does the analysis of the source program, generates the detects the errors, okay, generates the symbol table, and generates the intermediate code. And the back end actually, because these phases are considered as the back end of the compiler, the machine independent code optimizer, the code generator, and the machine dependent code optimizer, these are the phases in the back end of the compiler. They actually uh, synthesizes the uh, intermediate code and generates the target assembly code or the machine code. And the symbol table, you can see the symbol table is actually generated. Okay. And the symbol table is utilized both by the front end of the compiler and the back end of the compiler. As I have said earlier, that in the synthesis phase, the target program is actually synthesized from the intermediate code and the symbol table. Okay, now let us talk about the lexical analysis phase, which is the first phase of the compiler. So in the lexical analysis phase, the lexical analyzer or the scanner, as it is also known as the scanner, it reads the stream of characters, which is the stream of characters making up the source program, and it groups the characters into meaningful sequences known as lexemes. Now let us take the example of this source code, which is written in a high-level language. So this source code, you can see, is a stream of characters. Okay, position is equal to, see the statement. Position is equal to initial plus rate into 60. This statement is actually made up of a sequence of characters. This statement or this stream of characters is actually scanned by the lexical analyzer, and they are grouped into meaningful sequences called lexemes. I'll talk about what are lexemes in the latter part of this lecture. For each lexeme, the lexical analyzer produces a token. So these are considered as tokens. Okay. and they are passed to the syntax analyzer, that is the next phase of the compiler. The syntax analyzer is the second phase of the compiler. So tokens are actually generated in this phase, that is the lexical analysis phase. And these tokens are actually inserted into the symbol table. Now, how these tokens are inserted into the symbol table? In the symbol table, we have two columns. One is the token name and the attribute value. You can see these are tokens actually. So when the lexical analyzer scans the source program, okay, position is equal to the source code. You can see the sentence here. Okay, so position is equal to initial plus rate into 60. So here, the lexical analyzer actually scans the source, this stream of characters, and it generates the tokens. Okay, and these are the tokens. So the first, this position is equal to is actually grouped into a token. Okay, a token is actually generated for this. The token is actually an identifier. Okay, and its attribute value is 1. Okay, then this is an operator. Okay, this is an operator. So I'll talk in the later part of the lecture, I'll talk about what are identifiers. Okay, and what are operators and what are okay. So this is the second token. That is the identifier. Initial is considered as a token. So this is ID or an identifier, and the attribute value is 2. Okay, and then there is a plus operator. So this is an operator. So operator is also considered as a token. Then we have rate. Okay, so rate is also considered as a token, which is also an identifier. Okay, and the attribute value is 3. Then we have the product operator. So this is also considered as a token, and 60. This is also uh, considered as a token. Okay, so identifiers and literals are considered as tokens. Okay, so I'll talk about what are identifiers, what are literals in the later part of the lecture. So token is an abstract, token name is an abstract symbol that is used during syntax analysis. And the second component is the attribute value that points to the entry in the symbol table. So therefore, this value 1 points to the entry in the symbol table. That is, this identifier goes into the first position in the symbol table. This identifier goes in the second position in the symbol table. And this identifier goes into the third position in the symbol table. Now, blanks separating the lexemes. So these are basically the lexemes, and the blanks are basically discarded by the lexical analyzer. Okay, so you can see the symbol table is shown here. So ID is an identifier. This is an abstract symbol standing for identifier. And 1 is basically the position in the symbol table entry. Okay, the symbol table entry for position. Okay, so this identifier is entered into the first position. This is identifier entered into the second position. This is in the third position. Okay, and this is a number. This is entered into the fourth position. Okay, so and the operators, arithmetic operators, product operator, plus operator, these maps into tokens. So these are also tokens. Okay. Now the second phase of the compiler is the syntax analysis phase. So basically, the syntax analysis phase is also known as the parsing phase. So you can see in this parsing phase, the um, parse tree is actually generated here. So this is the parse tree, also known as syntax tree. So this syntax tree depicts the order of operations or the precedence of the operators. Okay, so the parser or the syntax analyzer uses these tokens which are produced by the lexicon analyzer to create a tree-like representation. Okay, and this tree actually depicts the grammatical structure of the token string. Okay, so the internal nodes, these are the internal nodes. Okay, these are the internal nodes. It represents the operations, and the leaf nodes represents the arguments of the operations. Okay, simply internal nodes will represent the operators will represent the internal nodes and the operands will represent the leaf nodes. Okay, and context tree grammar is used to represent the grammatical structure. So this grammatical structure, this syntax tree represents some kind of grammatical structure. So that is actually represented by represented using context tree grammar. Okay, so the third phase is the semantic analysis phase. So this in the semantic analysis phase, the syntax tree and the symbol table is used to check the consistency. Okay, so type checking is a major job of the semantic analyzer. The semantic analyzer checks whether each operator has matching operands. Okay, so here you can see the semantic analyzer. Uh, what it does is it applies a binary arithmetic operator. Okay, either to a pair of integers, a binary arithmetic operator, either to a pair of integers or to a pair of floating point numbers. If the operator is applied to a floating point number and an integer, the compiler may convert the integer into the floating point number. So here you can see this ID identifier 3 is basically a floating point. This represents the rate. Okay, so you have seen the source code. In the source code, this rate is basically a floating point number. So when you multiply it with a integer, you should actually convert this integer into a floating point number. So you should typecast basically. So this type checking is actually done by the semantic analyzer. So position is also a this floating point number, and the initial is also floating point number, and this rate is also floating point number. So when everything is floating point number, we need to typecast this integer 60 into floating point number and multiply it. So it is typecasted. This type checking is actually done by the semantic analyzer. So typecasting is performed in this phase, and this information is actually stored in the syntax tree. You can see that typecasting this into float uh, operation is done here, and that is represented by the syntax tree. And it is also this information is also entered into the symbol table. Now again, if we look into the phases of the compiler, so we have discussed about the lexicon analyzer, the syntax analyzer, and the semantic analyzer. Now we are going to discuss about the fourth phase. So that completes the front end of the compiler. So we are going to discuss about the fourth phase of the compiler, that is intermediate code generator. So in the intermediate code generation phase, the compiler constructs multiple intermediate representations. Okay, so these intermediate representations are various forms of intermediate code. So it's an explicit low level or machine like intermediate representation, which we can think of as a program for an abstract machine. Okay, so intermediate representation should be easy to produce and it should be easy to translate into the target machine code. So the intermediate representation is basically three address code. Okay, so three address code has three operands per instruction and at most one operand on the right hand side. At most one operator on the right hand side. So we shall look into the intermediate code representation of the, so this is the three address code representation of the same program that we are translating. So you can see here each three address representation has at most one operator on the right hand side. Okay, at most one operator on the right hand side. You can see here. Okay, so these instructions actually fix the order in which the operations are to be performed. Okay, so we can see the multiplication precedes addition operation. So the compiler generates a temporary name, okay, or a temporary variable. You can see T1, T2, T3. These are temporary variables to hold the computed value of the three address instruction. Okay, so you can see some three address instructions like the first in the sequence and the last in the sequence have fewer than three operands. Okay, you can see they have fewer, they have only one operand actually. Now the fourth, fifth phase of the compiler, that is the code optimization phase, uh, optimizes the or attempts to improve the intermediate code so that better code is produced or generated in time in terms of space and time. So a significant amount of time is actually spent in this phase. So mostly simple optimizations are tried out, which improves the code without slowing down the compilation process. Okay, so here you can see the code optimization which is being done here. So here you can see the the conversion of 60 from integer to float is done to eliminate this into float operation. Okay, so it is done actually in two lines. You can see two lines, which is actually earlier it was four lines. So these four lines have been optimized and it has been cut shorter. Okay, so a shorter sequence is actually sorted out. Okay, and finally the code generation phase, which is the sixth phase of the final phase of the compiler, which generates the assembly code. You can see this is the assembly code, which is generated out of the optimized intermediate code. So this is the assembly or the machine code or the target code. So registers and memory locations are basically selected for each variable used by the program. Okay, for each variable which are used by the program. For example, you can see the above assembly code actually uses registers R1 and R2. Okay, R1 and R2. Okay, so the first operand, so when you add floating R1, R2, that is the content of register R2 is actually stored into register R1. So the first operand becomes the destination here. Okay, so um, that's all about the different phases of the compiler. So we are going to talk about the lexicon analysis phase in details, and and basically the lexicon analyzer. Uh, how we shall talk about how the lexicon analyzer actually uh, generates the patterns. Okay, how the lexical analyzer generates the tokens. So it describes certain patterns using regular expression. Okay, and for a specific pattern, we can define a regular expression corresponding to a regular language. Okay, so basically, a stream of characters is taken as input. So this is the black box is actually the lexical analyzers. So there are patterns which are described using regular expressions. Now, when the input character sequence is actually taken here, okay, these patterns actually, uh, so for a specific pattern, a regular expression uh, is generated corresponding to a regular language. Okay, so regular expression is there, or a regular expression is there, which actually depends upon a regular language. Okay, and using this regular expression, the lexemes are actually constructed. Okay, now basically, what are lexemes? Uh, so these are basically the lexemes are nothing but the patterns, and the tokens. These are actually the tokens. Okay, so the tokens are actually classified into keywords, operators, variables, numbers, and white spaces. So if then is basically a token. So this is how it is represented. If then, okay, and else do is these are actually tokens. Else is a token. Do is a token. If is a token, then is a token. While is a token. Okay, so these are considered as keywords. So in a high-level language like C, when the lexicon analysis when the scanner or the lexicon analyzer scans the source program, these tokens are actually generated. Okay, these it scans. So if in the source program if there is a uh, character sequence like if, this is considered as a token. If there is a pattern like else, so these character sequences are nothing but patterns actually. Okay, so these patterns are actually defined using some regular expressions. So we'll talk about regular expressions and all these stuffs in detail in the later part of the lecture. While is basically a token. Okay. Then we have operators greater than operator. Okay. So OP comma GT. So this is considered as a token. Less than operator equal to operator. Okay. Then variables. So variables actually start with letters followed by digits underscores. So this is how we define a variable. Okay. So variable is also a token. Okay. Start with letters, digits, underscores. So identifier is variable. Okay. And then we have shown in the earlier example how we actually when we encounter a variable. Okay, so in the earlier source code you have seen point position is equal to uh, initial plus rate into. So position, initial, rate, these are actually considered as variables. Okay, so they are identified as tokens, and tokens are, I mean, variables are considered as identifiers. Okay, they are identifiers, and they have an attribute value, which is the pointer to the symbol table. And numbers, okay, uh, so they are also considered as tokens in white space. For white space, the lexical analyzer discards the white space. So no tokens will be created for white spaces. Okay. So thank you for